charge of the DOE, Department of Energy, fusion program at the time. 15 years ago, he started making public speeches saying, this was a gigantic mistake. We should not have narrowed the field so early. But it's achieved a bureaucratic momentum. Part of the bureaucratic momentum is because it's so gigantic. I mean, if you have a $20 billion or $30 billion international project, you've got contractors who are benefiting from those contracts, and at least in our country, I don't know whether this happens in England, that means political influence. If we go to Congress and say, give us money and we'll create 6 jobs in, Middlesex, New Jersey, we're not going to get very much traction. There is a, what I call anti-Darwinian tendency in government funding, that the most expensive alternatives are the ones that get funded. And there's a big benefit for a bureaucrat too, because it's much easier to administer a single large program than dozens of small ones, even though the dozens of small ones have a much better chance of success. So we've gotten to the point where, I mentioned we're circulating this letter, which people can view on our website, which is LPPFusion.com, which urges a broadening out of the fusion effort. And some people have told us, we can't sign this letter because we'd be fired for criticizing the direction of the program. So this is how a program gets solidly entrenched, even though it's really going in the wrong direction. Yes?
Hi, thank you for your talk. Just 2 small questions. So you mentioned, obviously, tungsten is quite expensive. Have you incorporated the the economics of tungsten into your costings for energy that you presented at the start? And secondly, in terms of criticism, I read a short piece on Mike Hopkins' blog that was questioning some of the results that you published in the physics of plasma. I was wondering how it responds to you.
Okay. Well, let me take the Mike Hopkins thing first. Mike Hopkins wrote on his own blog, not in a published peer-reviewed paper, that our results, quote unquote, weren't even wrong. And if you read down, basically what he says is they're nothing new. As far as I can see, Dr. Hopkins did not read our paper because he's criticizing us for something we didn't claim. He's saying we did not achieve higher fusion yields than other people had achieved. We didn't break through that plateau. That's because we didn't get the high density. That's not what the paper was about. The paper's title very clearly says we got record temperatures. We broke a record that had stood for about 40 years of how high temperatures this device can produce. And the level of temperature we achieved, technically, mean ion energy, was such that given adequate density, we could ignite PB11 fuel. So that's what we were claiming. We weren't claiming what Hopkins said we didn't prove, which is that we got higher density than everybody else. We clearly stated that our density was lower than many people had achieved. And in fact, it's the opposite. The fact that other people have achieved higher densities with the same device is one of the reasons we're confident we can achieve a higher density together with the high temperature. So as far as I can see, he just didn't read the article. And we are about to put a reply on our Q&A in our website. We would have, except we were suddenly invited to Oxford, so we didn't have time. The second question is about cost. Well, first of all, in a working generator, we would not be using tungsten. We'll be using beryllium, which makes the cost worse. But do I think it's an important cost factor? Probably not. First of all, the cost of even though beryllium is a monopoly priced substance, the actual cost of the beryllium in our electrodes is a small fraction, maybe 1/10 of the price that was quoted to us. They're quoting a very high price for simply the fabrication, the machining of the beryllium. Now, if we're producing millions of these devices, that machining is going to be a mass production process. The price is going to come way down. So I mean, as a rule of thumb, going from one-of-a-kind production to mass production results in at least an order of magnitude reduction. So I don't expect that these electrodes will cost, more than 20,000. Overall, we expect, with mass production, that the machine, with its energy conversion and everything else, will cost somewhere between $300,000 to $1 million, probably around $500,000. And if you do the numbers, you can see this ends up with a very small cost of electricity. Right now, 5 megawatts, by any means, the capital cost alone will be at least $5 million. So if you have something where the capital costs are much lower, and the fuel is essentially insignificant, because this is nuclear, the energy is coming from the nucleus. It's not what's commonly called nuclear energy, which is fission energy. But energy from the nucleus is extremely energetic. So the fuel for 1 year for a 5 megawatt generator is 1 kilo. Boron is a very abundant element. Hydrogen, obviously, is a component of water. So this fuel is going to be very cheap, an insignificant part. In fact, we expect the main cost of the energy that comes from focused fusion is probably maintenance. You're going to have these electrodes replaced, ideally once a month, maybe at the start, once every 2 weeks. There's going to have to be initially skilled people doing that replacement. They'll probably remove the cost. At some point, you could have robotic replacement. It would drive up the capital cost, but might be a saving in the long run. But the bottom line is we don't expect beryllium to be a terrible cost factor with mass production. It's a cost factor to us because it's one of a kind. Yes?
Are there any new technical problems you expect from the introduction of beryllium to your fusion reactor?
The only technical problems is that this sputtering rate, the part of the erosion we can't eliminate, will be somewhat higher for beryllium than it is for tungsten. There's no one ideal material because tungsten is great for everything except X-rays. Beryllium is necessary for the X-rays. So that will be a technical problem for the engineering stage. Over the billions of shots that these electrodes will have to last, sputtering will have to be controlled or adjusted for. In terms of the scientific experiment, we don't think that the beryllium will introduce any particular problems. So we're pretty confident that once we understand and are running well with the tungsten, when the X-rays get up to the level that we need the beryllium, we want to have the beryllium already available. And that's very important in terms of the timing. These tungsten pieces, we decided on this course of action in May of 2013, and we still don't have the tungsten pieces. It took this long to get a supplier to agree to do this. This is actually a large piece from pure tungsten. To work out the details, to agree on money, and so on, and to get the actual one-of-a-kind production done. So we don't want to have the same delay with beryllium. We want to have the money in hand now, and we'd actually start talking with the supplier to get this ready, so we would have it ready to go when we get to that stage, and that we wouldn't be having. I mean, we've had, waiting for the tungsten, the machine has actually been non-operational since, I believe it is November. So we've had a 6-month gap, and we'd like to avoid that with beryllium. Anything else?
How will you load your fuel into your reactor when it's operation? Does that go in gaseous state?
Well, the fuel we expect to use, there are a number of compounds of boron and hydrogen. We expect to use the compound called decaborane, which is 10 borons and 14 hydrogen. And that's a solid at room temperature. But because its boiling point is not very high, if you heat it up to about 100 or 120 sig, you get enough vapor pressure off of the solid that a canister of the solid attached to our vacuum chamber will fill up the vacuum chamber. Now that does mean that we have to keep the entire vacuum chamber at a pretty even heat above whatever temperature we need. So the whole thing, we've already specified what heating blankets we need to order to keep the chamber at about 120 degrees. So that's how it will be introduced. This is also a safety factor. The compound is somewhat toxic. So is gasoline. So for our own safety, it's very convenient to have it in a solid form, and therefore, when it's gaseous, it's under negative pressure, because of course, the pressure inside the vacuum chamber is much less than outside. So that means that when it's being heated up, it's incapable of leaking out. The other good thing about the compound is that it breaks down very easily. The exhaust gas, the unburned fuel, can be exhausted just through water, and then it turns into boric acid, which many people are familiar with as a household product. It's good for killing roaches, but it's not harmful to us. Well, if we're finished, we should make the announcement of what's happening